Hi, I am Sungjoon Park from Upstage, and with Jihyung, today I will introduce KLUE, which stands for Korean Language Understanding Evaluation. We are very happy to present our work to share our experience of developing evaluation system of language models. In this talk, we will introduce why and how we built KLUE benchmark datasets and further experiments upon them with our Korean pre-trained language models. Then we discussed ethical considerations and broader impact of our work. Actually, we published KLUE paper in arXiv, and that is 76 pages long, but we only have 30 minutes here, so we will briefly introduce each part of them. The background of KLUE is closely related to the recent natural language processing research trend. In 2018, ELMO only had 94 million trainable parameters, but after 3 years, GPT-3 reached a size of 175 billion of parameters, about 1,000 times bigger than ELMO. This is mainly because large models generally shows empirically better performance on downstream tasks, even with few examples. And all these models are pre-trained over English corpora and fine-tuned on English public benchmarks like GLUE or SuperGLUE as well. Many Korean NLP researchers and engineers are motivated from these progress, so that they soon replicated those models for Korean and open sourced the models like BERT. But there were a few existing Korean datasets to evaluate them properly. Actually, there were several limitations in existing resources in terms of diversity, accessibility, quality, and AI ethics. They usually lack diversity of task type, format, and domain of corpus. And most of them are too easy for fine-tuned language models, already being saturated, so there were almost no room for improvement. Also, license of datasets are limited. Redistribution or modifying them is prohibited in many cases, which prevents researchers with improving the datasets. Quality of the text and labels is another issue. Some of their labels are very noisy and have a lot of errors, and this is even more serious when their text is machine translated from English while the labels are simply copied from that of original datasets. In addition, in most cases, they did not consider filtering offensive content or personally identifiable information in the corpus. So we gathered as a team. KLUE team is a community-driven project group. Our objective is to establish common evaluation system of natural language understanding models and baselines for Korean. We designed and built a set of such benchmarks and the system from scratch, and further pre-training and fine-tuning Korean language models on them. Our team had 30 members from more than 10 institutions. 28 researchers and engineers came from 12 universities and companies, and 3 advisors guided this project to build them properly. 11 institutions sponsored us in many ways, with providing data annotation codes, cloud computing resources, licensed data for free, or supporting researchers. The project started in November 2020 and ended up opening by leaderboard in June 2021. Outcomes of this project are 8 KLUE benchmarks datasets and leaderboard, pre-trained Korean models as a baseline. They are available at Hugging Face Datasets and Model Hub. You can also access them through these URLs in this slide.
In this session, I'm going to talk about what we have aimed and done when designing and building KLUE, which consists of the 8 tasks: topic classification, semantic textual similarity, natural language inference, named entity recognition, relation extraction, machine reading comprehension, and dialogue state tracking. KLUE benchmarks are designed to overcome the above-mentioned limitations of the existing Korean corpora. We pursued KLUE to be diverse, accessible, quality assured, designed with suitable metrics, and to have few ethical harm. For the diversity, we choose the 8 tasks that include syntax and semantics tasks while addressing the needs of academia and industry. Accessibility and quality are important, especially for a benchmark suite, as the benchmark serves as a standard for evaluating and improving NLU systems. To prevent models from amplifying any toxic behavior, we proactively remove examples from both unlabeled and labeled corpora that reflect social biases, contain toxic content, or PII, both manually and automatically. In line with our design principles, we have actively sought corpora that are accessible, cover diverse domains and topics, have less ethical risks, and are written in modern Korean. As a result, we have collected 10 corpora, which are news headlines, Wikipedia, Wikinews, Wikitree, Policy News, Smart Home Utterances corpus named Para KQC, Airbnb and movie reviews, and news articles. All corpora are assigned to the above mentioned tasks considering a goal of each task. Before we get into the details of each task, I'd like to point out that two design principles, namely AI ethics and quality, mainly influence the construction process. For all tasks, we ask annotators to report any problematic sentences and try to make progress towards Korean NLP. Each and every metrics are not only designed to provide different views on a model, but also suitable for Korean. The evaluation sets are deliberately sampled to distinguish a well-generalized model and a model relying on a superior skew. Let's move on to the why not. Why not is a simple topic classification task. However, for Korean, no dataset had been proposed for the task, which motivated us to construct it. YNet was built upon almost equally sampled news headlines from the 7 sections. Different from the usual topic classification dataset, we manually annotated the label due to the clickbait or confusing categories. 3 annotators worked for a single headline and we kept the majority vote. We intentionally split dev and test set based on the publication date to not incentivize model which finds a spurious relation between a keyword and a label. Our metric is macro F1 score to weigh the same importance to each class. The second task, STS, is a regression task to measure the degree of semantic equivalence between two sentences. Although STS is essential to other NLP tasks such as machine translation, summarization, and question answering, translated STS dataset had been the only Korean STS dataset. Before the annotation, we carefully sampled or generated sentence pairs to have varying degrees of similarity from Airbnb reviews, Policy News, and Para KQC. For example, we generated pairs of Airbnb and Policy News sentences via round-trip translation and sampled pairs using greedy sentence matching with root scores. For Para KQC, on the other hand, we leveraged the labels to get both similar and dissimilar pairs. After the annotation, we looked into the annotated results and found similarity scores are skewed towards 0 and largely bimodal. Thus, we sampled examples for dev and test set to get uniform distribution over the score. We evaluate STS model with typical STS metric Pearson's R, an additional binary F1 score, reformulating STS as paraphrase detection task. Our third dataset, KLUE NLI, is a sentence pair classification task which infers the relationship between the hypothesis and the premise. Note that the only Korean NLI dataset had been translated as SNLI and MNLI. Following MNLI, we wanted ours to have multi-genre and use 6 different source corpora. We were aware that SNLI and MNLI are known to have annotation artifacts coming from human writing-based hypothesis generation. In such writing process, sentence lengths and explicit lexical patterns are easily related with certain classes. To minimize such artifacts and improve quality as much as possible, we prepared guidelines with specific do's and don'ts, rigorously trained the workers in advance, and validated thoroughly. Thanks to the efforts, we could make high-quality NLI dataset. The rate of anonymous gold-labeled examples in KLUE NLI is 18% higher than that of SNLI and MNLI, and 33% higher than translated NLI dataset. Also, individual annotators' agreement with the gold label and the author's label are higher than that of SNLI and MNLI, and almost all pairs received the gold label. When splitting dataset, our goal was to prevent our NLI benchmark from incentivizing a model that predicts a label using spurious Q in the hypothesis. So we trained a classifier using only hypothesis and then used its prediction probability score for the split. Specifically, we computed the distance between the prediction score distribution and the ideal distribution using cross entropy, extracted the sets whose mean distance is among the lowest 20%, and then randomly split them into dev and test sets. For evaluation metric, we adopt the same metric with SNLI. Our fourth dataset is KLUE-NER. We included KLUE-NER since there are few existing Korean NER datasets, although NER is an important for application fields like syntax analysis, goal-oriented dialogue system, question and answering chatbot, and information extraction. It was built upon both formal and colloquial corpora, while all of the Korean NER datasets had been built with formal corpus. As I like to highlight more on evaluation metrics, I'm going to skip the other parts. You can find more details in the paper. We used entity level and character level macro F1 score for the evaluation. The former is sensitive to a tokenization strategy. If a tokenizer fails to split stem and affix appropriately, as in the example, it never gets a high entity level score while earns character level score partially. Our fifth dataset is KLUE-RE. Relation extraction identifies semantic relations between entity pairs in a text. Thus, collaborating with NER, RE is able to construct knowledge base from the unstructured text. In the annotation process, we used distance supervision for some and without it for the other to take a best of both worlds. As there is no Korean knowledge base in Freebase skill, we built additional ones by parsing the info boxes in Wikipedia and Wiki to enlarge the pool of the candidate triplets. But when building the development and test sets, we only use examples without using knowledge base for real-world scenario. Also in the test set, we only include sentences with entities that do not appear in the training set. We chose to measure RE models with micro F1 and AU PRC scores. Micro F1 score gives each sample the same importance, thus naturally weighing more on the majority class, which is no relation in this case. We didn't want a model focusing more on predicting negative class. We calculate micro F1 without it. AUPRC, on the other hand, is a useful metric for this imbalanced data setting where important positive examples are rarely occurred. Sixth dataset is KLUE-DP. Dependency parsing aims to find the relations among words in a sentence, and we include DP in KLUE to evaluate the language models in terms of synthetic features. The dataset follows Kona format and contains part-of-speech information as well. For the source, we sample sentences from both Wikitree and Airbnb, and KLUE-DP was the first Korean dataset using colloquial texts. When labeling, we followed annotation scheme proposed by TTA rather than using universal dependency scheme, which is more appropriate for Korean. We first annotated part of speech on the corpus and used them when annotating the dependency relations. Both POS and DP were annotated by 10 Korean linguistics PhD students. We evaluate a model's performance with UAS and LAS. Seventh dataset is KLUE-MRC. MRC, as we all know, is to test models' ability to answer a question about a given text passage and has become an essential task in NLU benchmark since it is one of the most intuitive methods for measuring text comprehension. However, existing Korean MRC datasets are either less challenging, limited in access, or simply machine translated from an English dataset. Thus, we designed KLUE-MRC to overcome such limitations. In line with the efforts, we first used Wikipedia and news that can be redistributed with the desirable license. Second, we created a new challenging Korean MRC benchmark that provides multiple question types which hadn't been proposed for Korean, while preventing non-annotation artifacts. For MRC evaluation, we proposed a new metric, character level rouge, in addition to the exact match score. Exact match is the most commonly used metric for MRC tasks, and similar to the entity level F1 for KLUE-NER, tokenization matters. We adopt character level rouge score rather than F1 score, which is used in all the previous Korean MRC datasets since simple F1 score measures character overlap regardless of the meaning. When a model predicts great people in Korea and while an answer is limited scope, a metric should give a lower score. Root scores 15, which is quite low, whereas character F1 overscores due to the overlap of some characters. Our last task is dialogue state tracking, and we name the dataset OS, abbreviation of Wizard of Soul. Following a growing attention to a conversation system and a task-oriented dialogue system is one type of it, we included dialogue state tracking to KLUE benchmark. DST is about predicting the dialogue states from a given dialogue context as illustrated in the table. Different from the other datasets in our benchmarks, OS is not following an ordinary protocol. Rather, we collect dialogues and their corresponding dialogue states at the same time. We started from defining a task schema which expresses the scenario of task-oriented dialogue, then constructed a knowledge base based on the task schema of each domain to obtain a set of predefined candidates of a user's goal. To support the workers to perform such complicated work effectively and efficiently, we provide a graphical web interface with a newly introduced feature, drop-down components. Drop-down interface naturally prevents several types of annotation errors such as multi-annotations, misannotations, typos, and so on. With such materials, we adopt self-dialog scheme to collect dataset. Such scheme is more efficient in terms of the cost and time than employing two different annotators for each user and system side. Considering a real-world scenario, the evaluation set includes dialogues with counterfactual goals and unseen knowledge-based instances against train set. For evaluation metrics, we defined joint goal accuracy and slot micro F1 score. Joint goal accuracy measures the proportion of exactly matched dialogue states among the total number of dialogue turns. Slot micro F1 score is an average of micro F1 scores in each turn. Next, in this section, I'm going to introduce our language models and their fine-tuning results. Language model recipes are not special as we followed BERT and Roberta setting. However, our tokenization strategy and corpus preprocessing are worth to share. For our special ingredients, we further studied their effects on the downstream tasks and going to share in ablation results section. For the pre-training corpus, we gathered publicly available Korean corpora from diverse sources to cover a broad set of topics and many different styles of size, approximately 62 GB. We then removed sentences already included in our benchmark datasets using BM25. As continuously highlighted, we kept considering ethical issues. Therefore, we replaced 16 personal data types where any solid pattern exists. In contrast, we didn't filter out socially biased contests nor hate speech for 3 reasons. First, manual inspection is infeasible for this large-scale pre-training corpora. Second, it is a challenging problem on its own to automatically detect socially biased contents or hate speech, as both of these highly depend on the context in which they appear. Lastly, being blind to such harmful contents prevents the future use of a language model for detecting and correcting these harmful contents. For the tokenization, we wanted to respect the agglutinative nature of Korean, which is to say, a word is a constitution of stems and affixes. The stems tend to remain unchanged on different unions, and the boundary is generally clear. Although BP has been widely used across many languages due to its effectiveness, it struggles to identify morphemes correctly as demonstrated in an example. Thus, we designed and used a new tokenization method, namely morpheme-based subword tokenization. To be specific, when building a vocabulary, we pre-tokenize a raw text into morphemes using a morphological analyzer, and then we applied BPE to get the final vocabulary. In addition to our own language models, we evaluate 2 existing multilingual language models and 2 Korean monolingual language models on our benchmark. We found that Korean PLMs generally outperform multilingual PLMs, and there was a large gap between them on tasks like KLUE MRC and KLUE RE. Second, Korean-aware tokenization affects 2 sequence-tagging tasks like KLUE NER and KLUE MRC. Third, the large model ends up outperforming all other models in most tasks. To see the details of our fine-tuning method, you can follow the link below. We analyzed the impact of our two choices, the corpus pseudonymization and the tokenization strategy. Our finding shows that corpus pseudonymization brings some drop in a subset of the tasks, but such drop is quite minimal. This suggests that the minimal level of pseudonymization is already a good way to balance the task performance and the risk of leaking private information. For the tokenization strategy, we contrasted our tokenization against the standard BP and found significant differences in the task performance in the cases of KLUE NER, KLUE MLC, and OS, which proved the impact of suitable tokenization.
This is the last part of the talk, here discussing ethical considerations in building KLUE benchmarks and models, and their broader impact and limitations. Summarizing ethical considerations. First, we thought copyright and accessibility of the benchmarks and models are important for properly using the resources. We released KLUE under Creative Commons by Share Alike, CC by SA. This allows users of KLUE benchmark to copy, redistribute, remix, transform, and build upon it for both commercial or non-commercial purposes, as long as derivatives and distributed under the same license. For our language models, we collected publicly available corpora, but we are not redistributing the training corpora, unfortunately because we cannot guarantee that our corpora do not contain any copyrighted work. But for the models, the parameters of the language model are simply just numbers, so they does not express human thoughts and emotions. Therefore, they do not meet the requirement of the being copyrighted. Second, toxic content. For the datasets, we applied three stages to minimize such toxic content. We first trained and used toxicity classifiers to detect and remove them before annotation, and then we explicitly and clearly instruct annotators to mark any instances that exhibit social biases or toxic content. Finally, we manually examine these marked sentences and exclude them. On the other hand, as mentioned in previous slides, pre-training corpora is too large for human investigation. Even we are using publicly available corpora, we cannot guarantee such content is completely removed. Since it is very challenging to build a perfect automated tool to detect hate speech and biased sentences, we decide to use pre-training corpora as they are without distributing them. We envision the future in which these pre-trained language models are used to build better tools for automatically detecting various toxic contents. Third, we care about personally identifiable information. It has recently been discovered by that a large-scale pre-trained language models memorizes a large amount of PII and that an algorithm can be designed to retrieve those information. In the case of the task-specific datasets, we rely on manual inspection during annotation to detect PII. We discard any sentences that were reported to contain them after the inspection. For pre-trained corpora, we pseudonymize 16 PII types that are detectable purely by rules through using regular expressions. Broader impacts and limitations. We distribute KLUE under CC by SA license. This allows using our datasets for any purpose, derivative work, and redistribution. Redistribution is crucial because it significantly limits research if sharing the datasets with another is prohibited. This is mainly due to the license of source corpora. If a benchmark is built over such text corpora, copyright infringement might occur when distributing them. In other case, if the original author does not allow derivative development of the benchmark, other researchers cannot improve it, for example, by removing toxic content or building a more challenging dataset to accelerate research for the technical improvements. If commercial use is not allowed, researchers working at for-profit organizations would not be able to benefit from nor to easily contribute to the benchmark. We hope above three factors facilitate Korean NLP research. We also open our pre-trained Korean language models and the implementation of the pre-training and fine-tuning pipelines. This enhances reproducibility of our work and allows anyone to fix and improve our data and models. And finally, one of the limitations of our work is lack of overall performance metric of all 8 tasks. We do not average all scores gained from each task in KLUE because the performance of all tasks are measured by different evaluation metrics. In this situation, simply computing the average of all tasks as in KLUE results in misleading overall performance measure. The average will lose its interpretability as well as giving higher weights to a certain task in unintended ways. Recently, analyzing correctness of a model's prediction by using item response theory framework to estimate such capabilities proposed, however, we find that it's not clear how it should be applied precisely in our benchmark. As of now, we thus decide to evaluate a model for each task separately without any summarization of overall performance measure. This is our limitation, and we leave this problem for the future. Thank you for listening. If you have any questions or suggestions, we are happy to take them. See you in the other time.